Chances are you are watching this program via satellite in one way or another, either transmitted directly or indirectly to your television, iPad, laptop or phone. In other words, you're using technology once considered science fiction. Pushing the envelope, technology must keep up with demand. More data, more reliability, and real-time connection. Space-destined hardware and technology are on the cutting edge of science, often introducing new methods of gathering scientific information. Demonstrator missions are regularly sent up, flying new engineering solutions to prove the hardware in situ, even without a specific goal in mind.
Technology goes through a whole development cycle, which we call the seamless chain of innovation. We start from the idea and we work along to develop it through our work in the labs, through the work of industry, and especially of small and medium industries, which are the vectors of innovation. But at the end, you need to prove that it works in the real space. And in order to do that, we use these missions that can take the risk of flying unproven technology and demonstrate to the larger missions that they work.
Research laboratories focusing on the next generation of space hardware are dotted around the globe. The UK's Space Gateway Harwell campus, the ESA RAL Advanced Manufacturing Laboratory, supports cutting-edge research and development.
The purpose of the laboratory is basically to assess and pre-screen candidate materials and processes for future space missions. So this will guide ESA, as well as the space community, in focusing their technology investments in the right area.
The lab has extensive on-site testing facilities, such as the ISIS neutron source, the Diamond Light Source synchrotron, and the UK's Central Laser Facility. This year will bring the first launch of a satellite using the small GEO platform, Hispasat 36W1. Small GEO, a telecommunications platform accommodating a wide range of payloads and missions, has been developed in Germany in a public-private partnership between ESA, OHB and the operator Hispasat.
It indeed, because Hispasat and ESA were able to join forces, that we were able to develop a satellite with such a level of innovation. On the one hand, a new platform with a new satellite prime contractor, on the other hand, a payload embarking also a high level of innovation. And altogether, this satellite has been developed, is going to be flown, and we provide very innovative services. So end-to-end, the level of innovation is very high, and indeed, separately, neither Hispasat nor ESA would have been able to undertake such a complex development. With the small GEO, what we have tried to achieve was really to develop a new product in the low end of the telecommunication market. And at the same time, this new product would allow a new prime contractor to become a prominent player of the satellite telecommunication market. That's the OHB, which is the prime contractor of this satellite.
This is a class of satellites that only have electric propulsion on board, which is a high-efficient system that allows achieving important mass savings. So we are able to put in space a satellite with a similar capacity of a full chemical one, but with much lower mass, which means less launcher cost, compatibility with more launch vehicles. And again, this translates in advantages for the operators who have at their disposal more efficient technical solutions for their mission. But it's very flexible, so it can also be used for other geostationary applications.
Another scheduled event in the telecom area is the launch of EDRS-C, expected by the end of the year. EDRS-C is also based on the small GEO platform and will be the first dedicated satellite for EDRS, the European Data Relay Service. It will be the second element of the Laser Relay's Space Data Highway. Low Earth satellites encumbered with line-of-sight communications can beam their data upward to geosynchronous satellites via laser, which can then transmit the signal to ground stations at any time.
The small GEO program is just the first step for OHB. OHB has already sold a number of other telecommunication satellites, and indeed this is the start of a product line that will evolve over time, like any other product lines of the other prime contractors operating in the satellite telecom market.
Another area of research has been in cost and time effectiveness in developing satellites. This has led to the CubeSat, several of which have flown in space. Measuring just 10 by 10 by 10 centimeters, these small cubes or nanosatellites have become extremely popular, opening up new possibilities for a wide range of groups previously unable to access space.
We are a small group of students with 2 professors and 2 coordinators, and we had 52 students who did the master's thesis on this project.
It's a great project for the students because it's the occasion to apply practical stuff and not only the theoretical stuff they have learned at school.
Our satellite is the telecommunication satellite. We use the D-Star protocol for the radio amateurs to communicate around the world.
This is really a special moment when we can see that finally the people is installed on the platform that will carry it to space on board the Soyuz launcher.
So it's a great feeling to be here in Kourou, in French Guiana, with the satellite almost in space and normally ready to roll.
Using off-the-shelf technology, CubeSats have been launched from the ISS and piggybacked onto other satellite launches. They will soon be deployed to Mars, asteroids, and further afield. GPS is used every day by people on the ground thanks to global positioning satellites from the United States. But GPS is not the only system in orbit. Russia has its GLONASS constellation, China has its own Beidou system, and Europe is building the Galileo network.
The initial services is a stage in the program whereby there is sufficient infrastructure is made available in space, satellites around the globe who circle around, plus infrastructure on the ground which control the satellites, provide the navigation signals. Enough of that infrastructure is ready so that the system can be used. The use is still not fully 100%, hence the word initial services.
These constellations are not exclusive. Galileo will also use the GPS system for even more accuracy, and the US is tying in with the Russian GLONASS for extraterrestrial services. In other words, they will enable spacecraft to utilize the positioning system in almost any orbit around the Earth.
Some of the signals are available only during a certain percentage of the day. The satellites move around and not all of the day you have sufficient satellites inside. But there is enough to start. And this is a very important moment in the program, an excessively important moment, because this actually shows to the world that the system is really going well. The performance we actually can provide, we know, is excellent. And of course we will continue building out the full constellation, but the users can actually now start using the satellite system.
The European Galileo navigation system is nearing completion. More satellites will be launched this year, adding to a constellation which will eventually number 22.
Under initial services, there will be 3 services provided. One is the so-called open service. This is for the mass market. This is where people will use their smartphones, their navigation devices in cars, which will have Galileo-enabled chips inside, which will receive both Galileo and GPS in combination, and it is the combination of the 2 systems which will be used to determine the position of the user. For ESA and the European Commission, when we started with satellite navigation, it was of course not quite clear how really important satellite navigation was going to be. And we had studies, we had our insights in it, and we knew that it would be important. But now we really see how important it is, particularly looking in the future, where we're going to need to have a sufficiently developed satellite navigation infrastructure to support autonomous driving and all sorts of other applications.
NASA has already developed specialized GPS receivers for space application. The Navigator receiver from NASA's Goddard Space Flight Center first flew in 2009 and proved to be very successful. A number of future missions in HEO, GEO and MEO plan to work with this receiver using its high-sensitivity signal acquisition and tracking capabilities. NASA's JPL has also developed a Blackjack flight GPS. Now being flown aboard an Argentine satellite, the system looks at how the GPS radio signal is distorted or delayed along its path. A typical GPS signal can plot a position to within around 22 yards. Blackjack can pinpoint its host satellite continuously to an accuracy of about 1 inch. 18 receivers are on orbit, while another system under development called the Triple GNSS or Tri-G will be able to track GPS and GNSS signals, including the Russian GNSS and European Galileo navigation constellations. All of our spacefaring nations continue their Earth observation work in collaboration with a number of organizations. The refinement of orbital positioning and unhindered high-speed communications mean more new technologies craft are being added to the armada of observation satellites. They include Europe's Copernicus program with no fewer than 3 Sentinel satellite launches. In March, Sentinel-2B will be launched carrying a wide-swathe, high-definition multispectral imager. With Sentinel-2A already on orbit, both Sentinel-2 satellites will monitor land cover, vegetation and water pollution.
Now that we get Sentinel-2B to fly together with Sentinel-2A, there's a couple of improvements that we get so far. We have a revisit of 10 days. With Sentinel-2B, we will have a revisit of 5 days. That means we see every spot on Earth every 5 days. That will help, of course, also to avoid the clouds or to have the chances higher to have no clouds in the various regions of the world. Both together, Sentinel-2A and 2B will also improve the performance of the services that are using the data.
Sentinel-2B is contributing to a constellation of Sentinel satellites, which really provides data over decades in different domains and with different instruments on board. So therefore, we're building up a fully operational system, which is enough incentive for industry to invest and to rely on this information in the future.
Sentinel-2A is already supporting a lot of applications. They're ranging from, for example, agricultural applications where we can do yield forecast to forest monitoring where we, for example, see deforestation. And besides that, there's plenty of other applications like inland water where we can look at the quality of the water. We can support river monitoring, but also coastal areas where we look at the changes in the coastal regions. On top of that, we recently changed also to acquire the Antarctic region, so we're also now looking at ice and glaciers.
Later in the year, 2 more Sentinels, Sentinel-5P and Sentinel-3B, will follow. The Sentinel-5 precursor mission is a satellite dedicated to monitoring our atmosphere at a high temporal and spectral resolution. It also offers increased cloud-free observation.
A second satellite, which is a replica of the first one, is of course shorter to develop and to test. The main effort when you develop a new system is put on the first spacecraft, where you discover basically all the early problems in equipment production, software validation, integration and test. All the specifications, plans, test procedures are ready whenever you start building your second spacecraft. And this is, of course, a large benefit. The second spacecraft, let's say, was realized in 1.5 year time. The cost as well, of course, of a recurring spacecraft is much cheaper than a proto-flight spacecraft. You could say basically it's 50% of the price of the first one.
Sentinel-3B is a multi-instrument mission to measure sea surface topography, sea and land surface temperature, and ocean and land color.
We are addressing a number of issues that relate to the development of new science, but also operational missions. For example, Earth Explorer missions, the scientific missions, but also we are preparing the next generation of Sentinel missions for Copernicus. In the next 5 to 10 years in Earth observation, we will face a number of challenges, some of them coming from outside. Big data, constellations, commercial companies entering our domain. And I think there we really have to see, as ESA, as European Space Agency, a public institution, how we can best react to these external challenges and position ourselves with our programs to really address these challenges from our perspective.
Demonstrating new laser technology, ESA is launching the ADM Aeolus satellite. ADM stands for Atmospheric Dynamics Mission. It will provide global observation of wind profiles. With this mission, ESA hopes to further our knowledge of the Earth's atmosphere and weather systems. hardware is orbiting Earth, it can only make scientific observations. Only our human perception of the beauty that lies below can help us fully appreciate the planet we call home.